Chapters 17 and 18, Phases and the Laws of Thermodynamics. Here is the overview. We will first talk about ideal gases, then move on to kinetic theory, which is an application of ideal gases. Then we'll talk about latent heat, define the first and second laws of thermodynamics. Then we will talk about thermal processes and how these are relevant to the first and second laws. Then we will talk about heat engines and the Carnot cycle. We will define entropy, and the final thing will be the definition of the third law of thermodynamics. Gases are typically the easiest type of matter to describe in terms of deriving physics equations. The easiest of gases are ideal gases, which all exhibit similar behavior. An ideal gas is one that is thin enough that the interactions between the molecules can be ignored, and that essentially means that the molecules travel through the gas and they don't hit other gas molecules. Now we will discuss some properties of ideal gases. The first is that if the volume of an ideal gas is held constant, then we find the pressure of the gas will increase with temperature, and the increase is linear since the pressure will be a constant times the temperature. We denote the volume as V, the number of molecules N, the pressure as P, and the temperature as T. An example of this is a car tyre. If you measure the pressure in a tyre at a particular temperature, and then the weather warms up and the tyre temperature increases, if you then measure the pressure again, you'll find that the pressure is bigger. Another property of an ideal gas is that if the volume and temperature are kept constant, and then we decide to add more gas into the ideal gas, the pressure will increase. We have an example on the right where somebody pumps up a basketball. We increase the pressure within the basketball, which makes it more firm simply by adding air via the pump. This is also the case for the tyre in a car or a bicycle, where we make the tyre more firm by adding more air. The pressure in an ideal gas is equal to a constant times the number of molecules. So when one increases the number of molecules, we can see that the pressure will increase. This is applicable for a fixed volume V and a fixed temperature T, as mentioned before. Finally, if the temperature is held constant and we decrease the volume, we increase the pressure. Here we have an example on the right when somebody sits on a basketball. This reduces the volume, and if you press onto the basketball, you find that it will be more firmer, and that's simply because the pressure has increased. The pressure is related to the volume inversely, and that is that the pressure is equal to a constant divided by the volume, again for the case where we have a fixed number of molecules N and a fixed temperature T. Now, when we combine all of these observations, we can relate the pressure to the number of molecules, N to the temperature T, to the volume V. It turns out that the pressure will be equal to a constant K times the number of molecules times the temperature divided by the volume. K is the Boltzmann constant, and that is equal to 1.38 by 10 to the minus 23 joules per Kelvin. And when we rearrange the initial equation, we get something called the equation of state for an ideal gas, which states that the pressure times the volume, P times V, is equal to the number of molecules, N, times the Boltzmann constant, K, times the temperature, T. An equation of state is something that links the bulk properties of the gas together, such as volume, pressure, the number of particles, and temperature, etc. And this is an example of an equation of state, which is the one that we use for an ideal gas. Now, experimentally, the number of entities, which we sometimes refer to degrees of freedom, which just refers to either atoms or molecules in the ideal gas, in a mole is given by Avogadro's number. And this is essentially the number of molecules in a single mole, and it's referred to as Na, and it's equal to 6.022 by 10 to the 23 molecules in a mole. Therefore, the number of molecules or atoms in a gas N will equal the number of moles, small n, times Avogadro's number, which is again the number of molecules in a mole. Avogadro's number and the Boltzmann constant can be combined to form something called the universal gas constant. This is represented by R, and it's simply equal to Avogadro's number, Na times the Boltzmann constant K, which is equal to 8.31 joules per mole Kelvin. And we can use this in an alternative version of the equation of state for an ideal gas, which states that the pressure times the volume, PV, is equal to small n, the number of moles, times the universal gas constant R times the temperature T. Now we will discuss kinetic theory, which is something that helps us relate microscopic properties of the gas, such as the position of gas molecules and the velocity, to the macroscopic properties, such as the pressure, the temperature, the volume, etc. There are three assumptions used in the kinetic theory that we'll discuss now. The first is that the molecules, which are represented by the number n, are identical, which means they have the same mass within a volume V, and the molecules themselves act as point particles. The second assumption is the molecules move randomly and will obey Newton's laws. The third assumption is collisions with the molecules are elastic, which essentially means that when the molecules collide with a wall, they will not lose any kinetic energy. Pressure is defined as some force per unit area, and the pressure due to a gas simply comes from molecules that hit the wall and then change direction. When you have a change in momentum, which is what's happening here, you have a force from Newton's law, and that force gives us the pressure. The example we have is a molecule that has momentum Pix. It moves towards the wall with minus mvx, and when it hits the wall, it has a final momentum which has a different sign, which means there has to be a change in momentum, and that is equal to positive mvx. The length that it will travel in this process, if it starts from one wall, hits another, and then comes back to the original wall is 2L. Now we can show what this pressure will be. As mentioned before, pressure P is equal to the force per unit area, so F divided by A. And from the change in momentum, we can show that that force will be mvx squared divided by L, and the area we can show will be L squared, and we can rearrange this further to get a pressure that will have to equal mvx squared divided by V. Not all molecules in the gas will have the same speed. There is in fact a distribution of speeds. This distribution is represented by something called the Maxwell distribution, which essentially tells us the speed versus finding a molecule with that particular speed, i.e. the probability of finding a molecule with that particular speed. We have an example on the slide. This distribution will essentially depend on the temperature. So for lower temperatures, on average, the particles that we find will have a smaller velocity. For higher temperatures, usually when we find a molecule, it will have a higher velocity. The most common velocity, or the velocity that's most likely, is represented by the lines, and we can see these are different for different temperatures. For the temperature of 300 Kelvin, this will be around 400 meters per second. The most probable velocity for 1100 Kelvin will be around 750 meters per second. Now we can replace the speed in the previous expression for pressure with an average speed. Since we have lots of different speeds, we can use an average instead. What we use is the average of the square, which is represented by open bracket Vx squared close bracket average. And when we consider the other two directions, we can come up with a final relation for the pressure, and that will equal 1 over 3 times N over V times M times the average of the square of the speed. This is telling us that the pressure in a gas is proportional to the average kinetic energy of the individual molecules. If we use the ideal gas law, we can then determine how the average kinetic energy relates to the temperature. This is represented by Kav, or the average of open bracket half mv squared closed bracket, and that is equal to 3 over 2 times K, the Boltzmann constant, times T, the temperature. The square root of the average of the square, open bracket V squared closed bracket, is called the root mean square, since we square something, take the mean, and then take the root. Now, if we solve for the RMS speed, which is equal to the square root of the average of the square, VRMS, which this represents, is equal to the square root of 3 times K, the Boltzmann constant, times T, the temperature, divided by the mass. We can see from this expression that the average velocity depends on the temperature in a way that when the temperature increases, the average velocity will increase. Conversely, if we increase the mass, that will decrease the average velocity. here we have a Maxwell distribution of velocities. The RMS is a type of average, essentially. There is something called the arithmetic average, which is the simplest type of average one can calculate. You simply add up all the speeds and divide by the number of molecules, and that's represented by VAV. And there's another type, which is VMP, and this is the most probable speed. When the distribution will have a width, all these things will be different. The RMS will be bigger than the usual average, and the most probable will be smaller than both of these. The internal energy of a gas is simply the sum of all the kinetic energies of all of the molecules, and in the case where each molecule consists of a single atom, this is represented by U, and it's equal to 3/2 times N, the number of atoms, times K, the Boltzmann constant, times T, the temperature. Now we'll discuss latent heats. It turns out when two phases coexist, the temperature can be the same even if a small amount of heat is added. What happens is the heat in form of energy goes into changing one of the phases to another. So in this situation, instead of raising the temperature when we heat something, it goes into changing the phase of the material. An example is melting ice. So ice you can raise to a temperature of 0 degrees Celsius, and when it turns into water, that water will also be 0 degrees Celsius. To melt more ice, you can add more heat, and that will get more water, but everything still remains at 0 degrees Celsius. So one needs heat to change from one phase or state of matter, which in this case is ice, compared to another phase or state of matter, which in this case is water. On the bottom, we have a more extensive look where we look at the temperature of ice, water, and water vapor, and we look at this as a function of the heat added. For the regions where we see a plateau, the energy is used to change the phase, either from ice to water or water to water vapor. For the regions where we see a slope, the heat is used to increase the temperature. As mentioned, heat is required to convert one phase to another, and we refer to this as the latent heat. And during the conversion process, the temperature will remain constant. The latent heat is specifically defined as the amount of heat one needs to change 1 kilogram of a substance from one phase to another. This brings us on to the definition, and the definition relates to the amount of heat one needs to add Q, and it's equal to the mass of the substance times the latent heat of the substance. The latent heat of fusion is defined as the amount of heat one needs to transfer from a solid to a liquid. The latent heat of vaporization is the amount of heat we need to transfer from a liquid to a gas. Here we have some examples in table 17.4 for various materials. What we see typically is the latent heat will depend on the material, and it also depends on whether you're talking about the latent heat of fusion or vaporization. For example, for water, one needs a greater amount of heat to convert 1 kilogram from a liquid to a gas compared to a solid to a liquid. Now we'll move on to chapter 18, and in particular the first law of thermodynamics. The first law of thermodynamics is essentially a statement of energy conservation, and it tells us that when we add heat to a system, we will change the internal energy. The change in internal energy, delta U, will equal some final internal energy minus an initial internal energy, and that will equal the heat. We have an example here where we start off with a gas in a cylinder. It starts off with an energy of Ui. We then add heat, and the final energy will be the initial energy Ui plus Q, and that final energy is represented by Uf. Work is another way that the internal energy can change. In particular, if a system does work on the external world, then the internal energy will decrease if no heat is added. We can represent this via the following. So the change in internal energy is equal to the final energy minus the initial energy, and that will equal the loss in energy, which is the work done, which is represented by minus W. Here we have an example of a gas that has a top which can move and a weight, and the gas essentially moves the weight upwards. In doing so, it will lose some energy, since that energy gets converted to the mechanical work energy that's used to move the weight upwards. When we combine these two observations, we get the first law of thermodynamics. This tells us that the change in the system's internal energy is equal to the heat added minus the work done by the system on the outside world. Now, it is very important to keep track of the signs of Q and W. When we add heat, Q will be positive. When the system loses heat, Q will be negative. When work is done by the system on the outside world, W is positive, and this results in a loss of internal energy. When work is done on the system, that means the outside world does work on the system and gives it energy. W will be negative, which means the contribution to delta U, the change in energy, will be positive. Now we will talk about thermal processes, which is an application of the first law of thermodynamics. We will assume that all these processes are quasi-static, and by that we mean that they are slow enough so that the system is always in equilibrium, and the implication of that is we can always describe it via the ideal gas law. We will also assume that they are reversible, and by that it means we can return the system to exactly the same state if we change it to another state while doing such a process. Here we have an example of a reversible process. We have a gas that is compressed and the temperature is held constant, and as it's compressed, heat will leave the system. We then allow it to expand. The top of the gas will move upwards and it draws heat into itself from the outside world, which we also refer to as a reservoir, and it eventually returns to its initial state with the same temperature, pressure, volume, etc. The work done by an expanding gas at a constant pressure is represented by W, and it's equal to the pressure times the change in volume. This is shown as an example on the left, where we have a gas with an initial volume VI and a final volume VF. The volume increases at a particular pressure P0, and that change times P0 is equal to the work done. We can also look to see how the pressure compares to the volume on a graph. This is what's shown on the right. We see that the pressure is constant and the volume changes. The area underneath the curve represents the work done, and this area will be the x-axis pressure P0 times the change in volume VF minus VI. If the volume stays constant, nothing moves, so no work is done. We can add heat to the system, but this does not change the amount of work done. And an example is shown where we have a container with pressure I, we add heat in the form of Q, and we get a bigger pressure, PF, but no work is done, since if we plot the pressure versus the change in volume, we just have a straight line. The area underneath this line is 0, so the work done will be 0 for the case where we have a constant volume. If the temperature is constant and the pressure varies, it will do so inversely with the volume. Here we have an example of some pressure versus volume curves for different temperatures. We can see as the volume increases, the pressure will go down, and that simply comes from the ideal gas law, where the pressure is inversely proportional to the volume. We can calculate the work done in this scenario, and it will be again the area under the curve, and for constant temperature, the work done, which is represented by W, will equal N, the number of molecules or atoms, times K, the Boltzmann constant, times T, the temperature, times log of the final volume divided by the initial volume. We can do this in terms of moles and the universal gas constant, and in this case the work done will equal the number of moles, small n, times R, the gas constant, times T, the temperature, times log of the final volume divided by the initial volume. Again, this calculation represents the area under the curve, which is the lighter shade of purple on this slide. An adiabatic process is one where no heat will flow into or out of the system. It will have a pressure versus volume curve that looks similar to the isothermal, and by isothermal we mean the same temperature is maintained, but it will be steeper. One way to ensure this is to insulate the system, so one can take this gas container shown on the bottom and one could decrease the volume. This will increase the temperature and the pressure. One can then expand this gas and the temperature and the pressure will decrease. In order to insulate the system, you have to make sure no heat flows in or out, so you can surround it by an insulator, or if this was done in a vacuum, then that would also insulate the system in the sense that there was nothing in the vacuum to exchange heat with the system. Here is a summary of all the different types of thermal processes that we have discussed. So for constant pressure, we can see the work done is equal to the pressure times the change in volume. One can rearrange the first law of thermodynamics to show that the heat will equal the change in energy plus the pressure times the volume. For constant volume, the work done is zero, which means the change in energy is simply determined by the heat. For the isothermal case, where the temperature is constant, the work done will equal the heat, and the change in the internal energy will be zero as a result. Finally, for the adiabatic process, where there is no heat flow and the temperature can change, the work done will be equal to minus the change in energy, and since there is no heat flow, Q has to be zero. The second law of thermodynamics relates to the direction of heat flow. We observed that heat flows always from something that is warmer to something that is cooler, and this means the direction of heat flow is one way with respect to the temperature differences. To state this formally, we say when objects of different temperatures are brought into thermal contact, the spontaneous heat flow that results always happens from the higher temperature object to the lower temperature object, and heat flow can never happen in the reverse direction. By that, it means we can never have heat flow from a cold object to the hotter objects, which would make the colder object even colder and the hotter object even hotter. A heat engine is something that converts the energy from heat into work. A classic example is the steam engine, and almost every single electricity generator that requires work to generate its current will get that work from heat. For instance, a coal power station, we get the heat from the burning of coal. A nuclear station, we get the heat from nuclear reactions that give heat. The idea is that we use, in a steam engine, fuel to heat water. The vapor expands and will do work against a piston. Then the vapor will condense back into water, and then we heat that water again to repeat the cycle. On the right, we have a diagram of such a process where we can see water is converted into steam. The steam moves around, pushes a piston, and then the steam comes back to something called a condenser. It then gets converted back to water, and a pump pushes this water back to the boiler in order to repeat the process. All heat engines will have a high temperature reservoir, a low temperature reservoir, and a cyclical engine. We have a schematic diagram on the right. The hot reservoir is used to heat something. This heat then goes into an engine, it gets converted to work, and the thing that is heated will then be cooled by passing heat into the cold reservoir, and the process will repeat. Now, in this engine, the amount of heat QH is supplied from the hot reservoir to the engine during each cycle. Some of that heat will be used as work, and the rest will be waste heat QC, and that will be given to the cold reservoir. The efficiency then is essentially how much work we get out, W, divided by the amount of heat, QH, which is the energy that we put in, and that is represented by E. We can also write the efficiency E as QH, the heat that goes in, minus QC, the heat that we waste, divided by QH, the heat that goes in, and this is equal to 1 minus the ratio of heat that is waste, QC, over heat that goes in, QH. Therefore, we can conclude in order for an engine to run, there has to be a temperature difference, otherwise heat will never be transferred. We can also express the maximum possible efficiency in terms of the temperature of the cold and hot reservoirs, and this will be represented by Emax, and that is equal to 1 minus the temperature of the cold reservoir Tc divided by the temperature of the hot reservoir Th. The maximum work an engine can do is therefore equal to the maximum efficiency, Emax, times the energy we put in terms of the heat, QH, which can also be expressed as 1 minus Tc over Th times QH. We can see that if two reservoirs have the same temperature, the efficiency will be 0 and no work can be done. And in order to maximize the efficiency, we want the biggest difference in temperature between the hot reservoir and the cold reservoir to push the efficiency as close to 1 as possible. Now moving on to entropy, which we can understand in terms of the heat exchangers and temperatures we discussed before for the heat engine. A reversible engine has the following relation that applies, and that is that the heat into the cold reservoir divided by the heat into the hot reservoir is equal to the temperature of the cold reservoir divided by the temperature of the hot reservoir. We can rewrite this and say that the heat in the cold reservoir QC over the temperature in the cold reservoir TC is equal to the heat from the hot reservoir QH divided by the temperature of the hot reservoir TH. The quantity Q over T, i.e. the heat exchange divided by the temperature, is the same for both reservoirs, and we refer to this as a change in entropy. Defining entropy change, which we represent by delta S, this is therefore equal to Q the heat over T the temperature, and it has units of joules per Kelvin. For this definition to be valid, the heat transfer must be reversible, and in a reversible heat engine, we can show that the net entropy change does not change itself, i.e. the entropy is constant. Now, a real engine will operate at a lower efficiency than a reversible engine. That essentially means less heat gets converted to work, and the main implication of this is when one determines the total entropy change, delta S, that will not be 0, that will be greater than 0. And this is defined by the entropy change associated with the hot reservoir plus the entropy change associated with the cold reservoir. An irreversible process is therefore defined as something that leads to an increase in entropy. The final topic is the third law of thermodynamics. Now, it turns out that the temperature absolute zero, or 0 Kelvin, is something that we can never achieve exactly, but we can get quite close to. In the lab, we have attained temperatures of 2 by 10 to the minus 8 Kelvin, but we have never got to absolute zero. And essentially, there is a technical challenge where reducing the temperature involves an exchange of heat, but that gets very, very difficult when things get very, very cold. This essentially leads to the third law of thermodynamics, and that is it is impossible to lower the temperature of an object to absolute zero in a finite number of steps.